So here I have a code. I wrote this code like to my book, like some time ago. That code is quite simple. I'm going to explain for you guys. So I have a matrix here which is new at the beginning. Somehow people tell me the sample size, the initial sample size to be considered, and this is n start, and the last sample size to be considered, which is like n point end, dot end, and here the number of dimensions we will consider. So if I have 2 dimensions, somehow when I start estimating for a sample size with this size, like n start, I will have to build up a space with data. This is like a random data space. As you guys can see, I'm just running a loop from 1 to r, as I have r dimensions. So I'm going to build up and bind those random numbers in terms of columns here. So this is the same as this. If I go to r and I do like okay, r norm, generate to me some random numbers with a Gaussian distribution whose mean is going to be equals to 0 and the standard deviation equals to 1, and I have a sample with for example 100 examples, and somehow I bind this with the same, let's say I have the same behavior now, the same distribution like that. So copy. Okay, this is going to be bidimensional. So if I plot that, I have something like this, right? If I have like a greater sample, probably 1000, it's going to be easier to see what's happening. Okay. So instead of 2, if I add up more dimensions here, like 3, 4, 5, I'm just building up a random sample, a random normal sample to test our classification possibilities, the number of distinct classifications we can build up on top of some data space or some input space. So this is just a random, a way of generating random samples, and on top of that I'm going to count the number of ways we can shatter the space, or the number of distinct ways we can classify that space. That's going to be used, that's going to be done with this list here. This is R, okay, but it could be another language, doesn't matter. So now I'm going to try for a number of iterations, and this is going to be a very big number of iterations, but later we can discuss that. I'm going to build up some hyperplane whose coefficients are defined in this line. So as you guys can see, I'm just defining a random hyperplane. Starting with, it's going to be a uniform distribution, starting with -1 and going to the range of +1. So in that situation, we have something like this. I build up from, for example, -1 to +1. In this case, if I have, for example, 2 dimensions, I have a hyperplane whose coefficients are -0.93 and +74. And so that's going to be multiplied by the terms I have to build up the hyperplane and see where it shatters the space, in which place of the space it is being positioned, and it will classify terms. And this is basically a bias to change the interception point of the hyperplane in terms of the input space. That's the same as having, for example, some sort of ax plus b function. So if I have 1 dimension, for example, if r is equal to 1 here, that would be my a in that situation, and the bias term would be this b. So I'm just changing the position of that hyperplane randomly, and every time after making that, I just apply that hyperplane on my sample, as you guys can see here. And this is a matrix multiplication, or I can see as a dot product, if you guys prefer. So I'm applying on top of that hyperplane and having the results here. So for example, if I have, just imagine, if I have like a matrix in which I have 1.11 and another -1, -1, and both are maybe 2 columns, and by row 2, yeah, I have something like this. So in one dimension I have 1, and another I have also 1. So rows are examples and columns are the attributes. So here I have -1 and -1. If this is my sample, and somehow I define my weights to be something like 0.5 and 0.5, for example, and my bias to be equals to 0, so that's the same as having my sample multiplied by W plus B. And as you guys can see, on one side of the hyperplane I have positive examples, on the other side I have a negative example. So this is going to be classified as positive, this is going to be classified as negative. If I have more examples, for example, if I decide like here to have another negative but a little far from the hyperplane, and another positive but far also from the hyperplane, in this case I have those guys are going to be far from the hyperplane. When I apply the same situation, as you guys can see, this is going to be positive, negative, negative, and positive, the classification. So it doesn't matter this number to me, because this number is like a distance from the point to the hyperplane. So instead of that, it's much more important, and that's why people, like in SVM, they use the sign function. Instead of that, it's much more important to know if I am on one side, on the other side of the hyperplane. If I have like positive or a negative example. So on top of that, I just decided to do exactly that. So I just get the results. Those are the labels, but they are like -5, -1, or +5, +1, as I showed before. When I do the switch, I just select the labels that are greater than or equal to 0 and save in this variable called ID. And the IDs and the negative values are going to be saved in this NID, negative IDs. So I just use like, okay, if it's positive, place +1. If it's negative, place -1. Instead of that, I could do something like this. Just apply the sign function here. And all of this, it's just not necessary, as you guys can see now. Because now I have just positive and negative values in these labels. Okay? So I decide to do this. I decide to paste all those values. If I paste those values, for example, these are the values, and I paste the values like that, take a look what happens. If I decide to paste the values with a separator like this, let me see if the separator, collapse. And collapse equals to nothing. It's going to join the elements. So I have like a key. That's the same as a hash key, a key for a hash table. So I decide to use that hash key to build up a hash table and count how many times that particular classification was built up. So after running that for several times, I'm gonna somehow fill out this hash table with lots of different possibilities of classification. At the end, I will just count how many classifications my random space had with this random approach. So it's more like an estimation for the shattering coefficient. It's not the exact shattering coefficient, of course. Okay, in that scenario, I just decide to do this. So somehow here, I can load my code and run this function. The name of the function is shattering coefficient estimator. And now I believe this is very important. Let's say I have like a space. I will start with a sample size equals to 1, and I go to a sample size equals to 20, only 20, or 25 maybe. And I run that for a bidimensional input space. That means I have 2 variables in the input space, right? And here I have an estimative. As you guys can see, if I have a single example, I can shatter, divide, classify in 2 ways. If I have 2, I have 4 ways of classifying. 3, 8, 4, it's 14. 5, it is 22, this is right. And afterwards, it's going to be just an estimation. But of course, it has some imprecision. but it's fair to do some initial experiments. So I could do the same for a different space, like opening a different command line here. So instead of running this, I will add up another dimension. And I think this is going to be interesting. So I will consider r equals to 3. You see, this should be 16, but as I have an approximation, it's not going to be exactly sometimes. And now it is, you see. It's just an approximation. But if I plot both, you see there's a huge difference. And that's the most interesting part now. I think it's good if you go to 20. It's not necessary to go after 20, I think, in my opinion. Maybe, yeah. Let's stop this. I will save this in a file and call it like r2.dat. It's going to be my file r2. And this I will save in another file. It doesn't matter if it's not 19 yet. I could run until 16. It's okay to have just an idea about what's happening. So R3, in both situations, I have a single hyperplane. Remember that, a single hyperplane. So I could open GNU plot now and try to estimate the functions. Before estimating, I will plot r2.dat and r3.dat so you can see what's happening. That's the difference in terms of the space of functions. So if I have a single hyperplane, I have less complexity, and this is the complexity measurement. And this is the complexity measurement for R3. So on top of that, I could do this. I could estimate a function like a times x to the square b x c. And I could estimate another function, could be like a g, and maybe h of x. And this will be like a coefficient d times x to the third, and e times x to the second, g times, because f is being used as function, x plus, I don't know, could be L, doesn't matter, 3, 2, 1, L, okay. Now I could fit this f of x in R2, dot via the adaptation of a, b, and c, the coefficients. Those are the coefficients. Those are the coefficients a, b, and c. So I'm going to save this so you guys can see there is an error. Of course there is an error because this is an estimative. So I could, sorry. Maybe like this, okay. So I could copy this guy and save coefficients for R2. These are the coefficients. And for R3, I need to estimate now for R3, and for R3 it will be, I just don't remember, yeah. For R3 it's going to be h of x on top of R3.dat via d, e, g, and L. Is that? Okay. Those are the coefficients. You see the error is greater, of course, because now I have more dimensions and somehow that the error is going to increase. But no problem. It's just a starting point. So now if I plot, take a look what happens if I plot R2, R3 together with the functions estimated on top of that. So I have an estimative for the shattering coefficient. That real-world estimative can be used to ensure learning and to understand the sample size. For example, consider this space. I'm gonna build up some space here with you. This is going to be the space. I'll have a random number generation here with a mean equals to 0, and maybe I could have a standard deviation equals to, I don't know, 0.2. So you have like 1,000 examples, and I decided somehow to have 2 dimensions. So I have this dimension paste. And all of those